Welcome to today's Explainer. So let's talk about how the apps we literally use every single day manage to take utter data chaos and turn it into lightning-fast results. Have you ever stopped to wonder what's actually happening right behind the glass of your screen?
Think about it. How does your favorite app find that one specific song out of millions and do it in just milliseconds? Well, imagine trying to find a single, tiny item in a completely messy room versus, say, pulling a perfectly labeled folder right out of a super organized filing cabinet. That right there is the core of what we're talking about today, the hidden structural architecture of our digital world.
To understand how these apps pull off this magic, we're going to look at the art of organizing data, compare arrays and linked lists, dive into searching and sorting, check out how to measure efficiency with big O notation, and wrap up with why this actually matters to you. All right, let's jump straight into Section 1, the art of organizing data and how we actually build these containers. At its core, a data structure is simply a designated way of organizing and storing data in a computer, so it can be used efficiently for different kinds of processing operations. I mean, you wouldn't store your milk in the pantry or your cereal in the fridge, right? Well, your machine is no different. It needs specific containers to process information effectively, whether that data is in a simple linear sequence or some massive complex hierarchy.
When we think about these fundamental concepts, like arrays, stacks, queues, and even more complex forms like binary trees and graphs, each shape solves a very specific problem. This isn't just a bunch of abstract math, it's actually the highly practical art of choosing the exact right tool for the job.
And that naturally brings us to Section 2, arrays versus linked lists, or, as I kind of like to think of it, choosing the right bookshelf.
So the two most common organizational tools start with arrays. Think of an array just like a highly organized, totally fixed bookshelf. The elements sit side by side in contiguous, adjacent memory locations. Because everything is right next to each other, you get constant time access. It is instantly fast to find an item if you know its exact position, literally like blindly grabbing the third book on the second shelf.
But if an array is a fixed bookshelf, a linked list is totally different. It's much more like a scavenger hunt, where one scattered clue explicitly points to the next. Now, this gives you awesome flexibility for dynamic sizing, because you just add a new clue whenever you need more space. But the trade-off is that it requires you to follow the sequence step by step from the very beginning to find what you're looking for.
With a linked list, each data node explicitly points to the very next memory address, forming that exact scavenger hunt chain we just talked about. A standard singly linked list ends in a null pointer, meaning it just stops, while a circular linked list loops continuously. It's a remarkably clever design. It allows for continuous traversal without ever needing to carve out a massive, predefined block of contiguous space on your hard drive.
Okay, so once our data is securely tucked away in these containers, how do we efficiently find what we actually need? Let's get into Section 3, searching, finding the needle, or flipping pages versus tearing the book.
The most basic search method is linear search, which just checks every single item sequentially. Imagine trying to find a specific word in a dictionary by literally flipping through it, page by page, word by word. I mean, sure, it works, but it's painstakingly slow. But then we have the much faster binary search, which continually divides the data right in half.
Binary search is an absolute game changer. But, and this is a big but, it works exclusively on sorted data. It selects the middle element and compares it to your target. It's basically like opening that dictionary to the exact middle, realizing the word you want comes alphabetically later, and literally tearing the book in half to throw the first part away. You just recursively repeat this until the element is found. You are instantly narrowing down your search in a fraction of the time. But of course, there's a catch. Since incredibly fast algorithms like binary search only work on sorted data, we need reliable ways to actually sort the chaos first. Which brings us to Section 4, sorting the chaos, putting things in order.
The absolute most basic approach to sorting is called bubble sort. In this method, the algorithm repeatedly steps through a list, compares adjacent elements, and swaps them if they're in the wrong order. The larger elements literally, bubble to the top through these repeated adjacent swaps. It's super easy to understand, but honestly, it's famously inefficient for large data sets. You would absolutely not want to sort a million user profiles this way.
So for massive lists, developers turn to divide and conquer algorithms like merge sort. Instead of comparing everything side by side, it breaks the entire problem down. First, it divides the unsorted list into halves. Then it conquers by recursively sorting each smaller independent sublist. And finally, it combines those sorted chunks back together into one single sorted list. It's a seriously efficient way to handle heavy data loads.
Now, we have all these amazing tools, but how do developers actually know which one is best for the job? Let's look at Section 5, Big O, Measuring Efficiency, where we prepare for the worst-case scenario.
To figure out which algorithm to deploy, developers measure efficiency using something called asymptotic analysis. More specifically, they look at Big O notation. Simply put, Big O gives us the mathematical worst-case scenario. It isn't about counting exact seconds on a stopwatch. Instead, it predicts how an algorithm's running time in memory space will scale as the amount of data grows from, say, a few hundred items to millions and millions of items.
When we lay all this out, it's basically a programmer's practical cheat sheet. For example, binary search scales beautifully at O of log n. That means even if your data grows exponentially, the time to search it barely increases at all. But on the flip side, bubble sort hits a dreadful O of n squared worst-case time complexity. Meaning, if you just double your data volume, bubble sort is going to take 4 times as long to finish. Yeah, no thank you.
All right, so the crucial point here is, why does any of this theoretical-sounding math actually matter to the software we rely on? Let's bring it all home in Section 6, Why This Matters, the real-world impact of DSA.
It matters because data structures strictly dictate our digital experiences. Just think about the actions you perform every single day. Stacks, which use a last-in, first-out method, are what give us the undo button in a text document. Queues manage our background downloads and printer jobs. Linked lists are the actual magic powering your seamless navigation through a Spotify playlist. And complex graphs, they're what represent our massive social networks and calculate the absolute shortest path on your GPS.
Choosing the exact right combination of data structures and algorithms is absolutely vital. Efficient code saves battery life on your phone, it reduces incredibly expensive server costs for businesses, and it prevents mobile apps from completely freezing up during heavy traffic. It's literally the subtle difference between an app that drains your battery and crashes and one that feels incredibly smooth and responsive.
It really just leaves you wondering about the invisible architecture running our lives. The next time your search results load instantly, or you seamlessly pull up a contact in your phone, just ask yourself, which unseen algorithms just executed perfectly in the background to save you hours of manual searching? Thank you so much for joining me for this explainer. I really hope it sparks a completely new appreciation for the digital magic happening right at your fingertips.